Ok. Vai começar a gravar?
Pode começar a gravar.
Vou deixar. Tudo gravando?
Gravando. Gravando aí, né? Cadê?
Gravando aqui, tá certo, tudo certo. Hi everyone, thanks for coming. This will be a brief overview of the history of the company up from the beginning to right now and our current plans. Okay, I was not planning to do this presentation, but we decided it would be a good idea to help everyone be on the same page to make this brief overview right now. So I'll be improvising. I hope we can do it in a single take, and I hope this help us understand where we are at and what are the current problems, the current mission, and the future plans of the company. Okay, so let's start. This is the brief overview of the higher company. Let's start with the origin. Okay, it all started when I was looking for a perfect language on my journey to studying computer science on the University of Rio de Janeiro. So I was looking for that, like, what's the best programming language in the world? What's the most efficient, the most high level, the one that will make me the most productive? And when I was doing that, I fell in love with the functional programming paradigm. Okay, so there are languages like Haskell, Clojure, Elixir, OCaml. Many of those languages are included in a group that's called the functional paradigm. I was falling in love with that paradigm. So that was when I started looking at it. And as I dig further and further, I started finding its flaws. Okay, so it looked very good, it looked perfect, but the ecosystem, the tooling, the user experience, the error messages, I have noticed that as good as it was in theory, it still had a lot to grow and to evolve and to improve in practice. And one problem in particular made me very puzzled, made me very confused. That was the fact that all those functional languages, they were running in a suboptimal runtime. Okay, so they are functional, they are made to run functions, that's what they do. It's a functional paradigm, it runs functions, and yet they compute those functions using suboptimal algorithms. That did not make sense to me, and that made me start looking for why that happens, and what are the existing solutions, the existing improvements for that situation. Okay, so this is a book that I was reading, like 7 programming languages in 7 weeks, when I was looking for like that perfect language. And then I found about this flaw, and then someone told me why all those programming languages run in suboptimal algorithms, there is an algorithm that's optimal, that can reduce compute functions as fast as possible in theory. Okay, that algorithm was based on a new model of computation. Okay, a graphical way to compute computer programs that was an alternative to the lambda calculus, to Turing machines, and that was capable of running functions optimally. Okay, so that model is called the interaction combinators. You can also call it interaction nets, small difference, but pretty much the same thing. It's an old paper from a researcher years and years ago. Okay, so it's a beautiful model of computation, and he proposes it as, like, in his argument, it's the ultimate solution to the problem of doing concurrent computations, doing parallel computations, and somehow it will also work it to reduce functions optimally. Okay, so it kind of looked like something new that I never heard about, like, what's that? I did not learn that in school. And that sounds so cool, because like it's something that can reduce the functional paradigm optimally and can also like do massive parallelism. So like 2 things in one, and just in a single framework, in a single model. I found that very interesting. Okay, I found that very beautiful. the way this model worked. I loved the Turing machine. I found it beautiful when I heard about it, but this looked like something different, and that nobody was talking about. So I was asking myself, okay, if it's so good, if it's like parallel, if it's capable of reducing computing functional language optimally in theory, why is nobody using it? Okay, so I spent some time looking at like the work that was done after this paper, and now the researchers and programmers that were involved with this idea. And the main problem is that while it was very fast, very good in theory, nobody managed to make a practical implementation that was competitive with the real world language that we had back then. Okay, so we have, for example, this site here, Computer Benchmark Game. It's a good website. I mean, it's not perfect. They make it very clear that benchmarks are very hard to do right, but it's an attempt at comparing like all those programming languages. So, for example, we have here C, Rust, C++. They are very fast languages. They are pretty much the backbone of the internet, computers, systems, everything like that needs to be very fast is built on those three languages. And we have some languages that are a little bit slower, but are still practical. So, for example, Haskell is a very good example that we use a lot. It's slower than C, but it's like almost as fast. It's practical. Many companies use it in the world today to build servers, to build products. Okay, so it's a good language, and it's not based on interaction combinators. Okay, it's based on a different model. So how did interaction combinators like this model of computation compare with those practical languages back then? It did not at all. Like it was hundreds of times slower. All the best implementations of interaction nets like would not even be on this chart. So, okay, good in theory, not good in practice. Okay, so that explains why people are not using it. But then why it's not good in practice? Okay, what's missing? Okay, so as someone that was studying computer engineering, I set myself to answer that question. Understand what's the, okay, it's good in theory, it's good like in the mathematics. What's missing to make this good in practice? To make it actually fast, okay, on real world computer programs, on real products, okay, on real software, okay? So I was set to answer up that question. So a few years after, when I was working at the Ethereum Foundation, okay, Ethereum like had many security problems, many issues that required more rigidness, more security, a lot of bugs, a lot of people like complaining that like the browser crashed and they lost money. That was a serious issue. So I managed to convince the Ethereum Foundation that we need to invest more time, more efforts in looking at the security problem. And one solution, I mean, not the silver bullets, but one solution that we had for security was to apply formal verification to contracts. And formal verification is a technique, okay, that is very closely related to functional programming language. Okay, so they use functional language to make programs, and then they use like that same language to prove that those programs are correct. So that sounds very useful for like Ethereum, for something that like smart contracts that you deploy, you can't remove later. So you need all the security. So like I convinced the Ethereum Foundation to start working on those formal verification projects, and inside that, we decided to build our language formality. Okay, that was a proof language that was targeting smart contracts. Okay, and while we were there, like making a proof language ultra secure, functional, I said, okay, contracts also need performance. They need to be fast. They need to use as little gas as possible because everything that happens on the blockchain has a real cost. Every operation counts. So why not try to use this optimal like reduction algorithm, this new paradigm on formality? Okay, so that's what I did. I made formality and based it on interaction combinators. Okay, so what were the results? Okay, this is my presentation on the DevCon 4, I believe, about this language. And here is, sorry, not this one. Let me go. Okay, so this is the result of doing like a computation on the formality language, okay, in a very high level program, a very functional program. So as expected by the theory, on high level programs, it was very fast, like something that Haskell took 20 seconds to compute and JavaScript took 9 seconds, formality took 0.29 seconds. So much less, very fast for high level, high order computations. But when you try to run something that was not like involving a lot of lambdas and high level stuff, so simpler things like lists and arrays, low level things, more like real world like programs, formality was not so fast. Okay, so I presented that. This number is not so happy. So like, for example, fleeting bits, okay, a low level code. So Haskell completed this benchmark in 2.8 seconds and formality completed it in more than a minute. So like as expected, turns out that this model of computation was great for high level, but still unproven for low level real world computations. Okay, so for a while, like there was not much I could do. Okay, I tried many optimizations. I tried to improve it as much as I could. I could not get formality in the same class of performance as like Haskell. And I mean, if I can't get it to be as fast as Haskell, that's like not the fastest language, there's no hope it one day would be like as fast as C, Rust, etc. Okay, so I was kind of stuck. Okay, I spent like a few years have passed. We did not have a lot of progress in this area. I started working in other things. Okay, so I guess it was like this presentation was in 2019. So 3 years after that, suddenly, like finally out of nowhere, I was not even focused on that problem, but I had an idea on how to change the memory layout of the formality language, okay? And based on that insight, I built a new version that I called HVM, Higher Order Virtual Machine, okay? So based on this new memory layout, that was itself based on a new take on interaction combinators that I called interaction calculus. Okay, so what's that? It's kind of new theory, okay, that I developed that's very similar to interaction combinators, but instead of being like a graph with a lot of triangles and things like that, I kind of turned interaction combinators into a calculus, like very similar to the lambda calculus, but with some small difference, like lambdas now have global scopes, everything is linear, and we have this incremental duplication operator that's based on like the triangle, like the node of interaction combinator. So pretty much I calculified, I don't know if that word exists, but I turned the graphical system in a calculus, and based on that new system, I wrote like a practical implementation in Rust, and I made some benchmarks, and it was way faster than I expected. Like I posted like this on Hacker News, like it spent some time on Hacker News, so a lot of people like was looking at it and curious about it, because again, the numbers, the results were like very good. So here, for example, we have a benchmark of the HVM on high-level computations against Haskell. Okay, so Haskell is the purple one, HVM is the green one. That's not an error. Okay, for high-level computations, HVM is much faster. Like interaction combinators are much faster, but that's no surprise. That's the kind of computation that it was already fast before. But again, that's not a like real-world common program. It's a very lambda calculus, high-level. It's not the kind of program that normal people write. But the good news is, in normal programs, so this is something more common, radix sort, sorting a list. It's something that many applications need to do every day, okay? So now, finally, for a normal program, a normal algorithm, we managed to have a performance that was similar to Haskell, okay? In the first benchmark that I made, in a single thread, I had pretty much the same performance as Haskell, okay? So from hundreds of times slower to the same performance as Haskell in a single thread. But we also had another trick, on the heads. Like, okay, if now I am on the same performance as Haskell, but if this model of computation is capable of massive parallelism, let's try to do that. Let's try to make this runtime parallel. And that's what I did. So with multiple threads, we managed to outperform Haskell. For the first time, this like interaction combinator, interaction net thing was able to outperform Haskell, not in a very lambda high-level program, but in a normal thing, like sorting in a big list, a very large list. So that was a great result, okay? And I was very happy about it. A few days after I posted this, like a lot of people have seen it on Hacker News, were commenting. So some people, of course, like from the functional community come, and they managed to optimize like the Haskell version that I have written. So turns out they made it 3 times faster. So in the final benchmark that we have here, Haskell in a single core is 3 times faster than the HVM, okay? But with 8 cores, the HVM becomes faster. So that's actually kind of cool, because the main point of the thing is not, okay, in a single core, in a loop version, in a loop computation with a lot of mutation, it will be faster than everything. That's not what's being claimed. What's being claimed is we have some kind of overhead. We need like some graphical overhead. So of course, it will never be as fast as C in a single thread. But we have a technology that's capable of scaling with cores. And we are in a world where computers are shipping with more and more cores. We have 12 cores in this computer. We have like GPUs that everyone's buying now because of the whole AI craze with 16,000 cores. So if you have a new model of computation that scales with cores, I think it's natural, I think it makes sense that in practice, this model of computation will be better than what we are doing now, because the language that we use now are made for a single core computer. Python, JavaScript, Haskell, like C, Rust, all those languages here, yes, they are good, they are fast, but they are made for a single core. So even if like this runtime is a little bit slower than this language in a single core, it's still a great result. Because like if with 2, 3, 4 cores, it's faster, then like in modern computers, it's faster, okay? So that's what I'm trying to do. So in the final benchmark of the HVM, like 3 times lower than Haskell, that's great to me. Like from 100 times to 3 times lower than Haskell and faster, okay, with multi-core. So that was a great result, and I was very happy about the first design of the HVM. So just to explain this graph, the green lines are HVM. So this is like HVM, the dark green line, HVM in a single core, HVM in 2 cores, HVM in 4 cores, and the purple line is Haskell. So that's what I'm trying to show. The more cores you have, the faster your program becomes. And you don't need to do anything else as a programmer, okay? The code here, like on Haskell and on HVM, pretty much the same code, okay? So very good. From the HVM, we had launched the kinds language. It was the successor for formatted lang, okay? So proof lang, very secure. We have the repo here. And as like expected, and I was also very happy about that, so I want to show that the successor of kindslang based on Haskell, we compare it to other proof languages on the type checking aspect, so the time it takes to verify the correctness of the program, and kindslang was much faster than everything else in pretty much everything that we tried. But that's, to be fair, because most proof languages are not trying to massively optimize the type checking performance, and I guess it's fair, okay? But I think there are uses for a very fast type checker, because if you're trying to do some type checking for AIs that need to train it in a loop, that's an application. But okay, just wanted to make this point that also not just on running programs, but on doing those type checking, proof checking on phase, it was also very fast. So okay, very happy about the HVM, built the formatted successor, kindslang, and then out of those two, we decided to found the higher order company. Okay, so that's the company that we have now. Okay, the idea is we have a great result here. We believe this technology can be used to make great things in the future. Let's build a company around it. Let's invest in that. Let's put some effort. Let's bring people to work on that. and try to make the best of this technology and see if we can extract real-world value, okay, of those things. Okay, so that's the goal of the hardware company. Okay, so that was so good. We made like some fundraising to like have a team, to have people working on it, and like finally we're getting to where we are now. That is, okay, we have the resources, we have the team. What do we do? Okay, so the first thing is I started like, of course, like look back at the HVM and asked myself, okay, what are the problems of the HVM? What needs to be improved? What can be done? Okay, so the most urgent things that need improvements. First, HVM was missing some important optimizations. Okay, so again, as I said, it's 3 times slower than Haskell in a single core. It would be like 10 times slower than C in a single core. But many things are not because like the runtime, the model of computation is limited and can't make those things faster. It's just that many optimizations were not implemented yet. So for example, we don't have loops. We don't have mutable arrays. And we can have that. There's nothing preventing us from having that. So those things, adding those things, would bring the single core gap closer. And again, the closer we are to those languages in a single thread, the better it will be when you use all the cores. It also was missing a lot of features, so like I/O, full lambda calculus coverage, which is something that's absolutely necessary if you want to compile like functional language to the HVM. We still did not have that, okay? So many features that were missing, but the main thing, the most important thing that was missing and that was critical, we can't live without that, was correctness, okay? So the current version of HVM, HVM1, it has a bug on the parallel version, okay? So when you run it with like trees, it works. When you run it like with 10 cores, it works fine. But there are some edge cases, like with a lot of lambdas, a lot of like church exponentiation, when you use a lot of threads, that it will hang. Okay, so it's a bug on the current implementation, and it's a bug that can be fixed. Okay, so it would be a lot of work, but we can fix it. But the problem is, while we have a bug, we can't like make it production ready. Okay, so because of that, like some people come to me and ask, okay, that's very cool. Can I use it in my company? No, you can't. Okay. Not yet. This is still a prototype. This is a research project, okay? Not ready for production. Can I use it on my academic research? You can, but like don't deploy it and expect that some bugs can happen. So not production ready yet. So what do we need to make it production ready? Okay, yes, we need some optimizations. We need like those features, but we need correctness, okay? We can't make this production ready before it's correct, okay? So we had 2 options. First option, we can work hard, like have a big team and have a lot of people like inspecting the HVM code and familiar with it, working on it and fixing those bugs and proving its correctness. But the thing is, if we did that, HVM is not complex. HVM is actually a pretty simple runtime, but it's not as simple as it could be. So suppose, for example, it has like the core has 3,000 lines of code. Example. So if you try to prove those 3,000 lines of code correct, it would cost an amount of time, it would cost an amount of money, okay? And the thing is, while HVM is not complex, I have the feeling that it could be simplified. We could reduce those 3,000 lines of code more, and if we did that, proving the correctness would be simpler, it would take less time, and finding new optimizations would also be simpler, okay? So the second option would be, don't make HVM1 correct and fast yet. Simplify it a little bit more, and then we can make it correct, make it fast. So pretty much, let's wait a little bit. Let's find what made HVM1 so fast, isolate those things, simplify, and then we work hard to make it as fast as possible, to prove its correctness. So I had the feeling that this would be the best direction. So I spent some time doing that, okay, trying to simplify the HVM a little bit more before I start like hard working on micro optimizations. And thanks to some new key insights that we had like this year, that I thanks also like the team that helped me a lot finding those insights, especially like Oliver that like had this great idea on how to do recursion with combinators. So we had a new design for the HVM, okay? It's similar to the old one, but some things change. So before, like to make it as fast as Haskell, we needed constructors, we needed global pattern matching, we needed many features. And now on the new version of the HVM, we don't need any of that. So we're back to interaction combinators, okay? It's even simpler. So like we went from interaction combinator to a more calculus-like presentation. And now we are back to interaction combinator. It's simpler. And we managed to do the same things that the HVM1 did, okay? So that's great. Less lines of code and can do the same things as the HVM1. So the challenge is, can we make HVM2 as fast as HVM1, okay? With this new like super combinator plus interaction combinator design. So I tried to implement it in Rust. I benchmarked it, and on the very first benchmark, it was faster than the HVM1, okay? So yay, we now have much less code, and it's faster than the HVM1 in this benchmark, okay? So I think I can, let me, just to make a little like live demo here. So this is the HVM program that we tested. This is not a Lambda calculus program. Okay, while it looks like a high-order Lambda calculus program, but it's a more like normal program. It's just like doing a lot of allocation and then doing a lot of XORs. Okay, so Boolean, bit things, like low-level things. Like does not look like, but it's more like a low-level stress test. It's not a representative test of everything. I did not have the time to make like radix sort and like and more complex things. Like it's very new. Okay, so the test that I could do is that one, but that's enough for this purpose because I'm testing against the HVM1. Okay, so this is the HVM1 normal program, normal benchmark. Okay, allocating a big tree, doing a lot of pattern matchings, doing a lot of XORs. Okay, so this program, it takes 4.4 seconds on the HVM1, first version of the HVM. Okay, so now I'll run on the HVM2, same program. Okay, different file. Now I'll just use the HVM2 compiler. Okay, same program. Let's run it. 1.4 seconds. Okay, so in this program, the HVM2 is all fine. Okay, so in this program, the HVM2 is 3 times faster than the HVM1. Okay, we still did not implement all things that HVM1 can do, of course, but this is a strong signal that with this new design, we can like reach the same performance as HVM1 and then improve on that. Okay, so and like and again, the cool thing, I mean, I was not expecting that. I mean, okay, I was kind of expecting that, but because now this new like design is so much simpler, reasoning about the correctness becomes much simpler, and reasoning about the correctness of the parallelism, that's the hard part, also becomes much simpler. So okay, same performance, like actually faster than the HVM1, very good, simpler design. Let's try to make it parallel. Okay, so but why on the CPU? Because like the HVM1 was on the CPU, 10 cores, and no way I would be able to implement HVM1 on the GPU without like a lot of days or weeks of work, because like it's not complex, but it's not so simple as that. So I never managed to implement the HVM1 on the GPU. So I was like, okay, let me try to go directly to the GPU. Let me try to run this algorithm in thousands of cores. Can I do that? Can I make it work? I was not sure I would be able to, because again, to make something work with thousands of cores, you need to have it correct, okay? Because, I mean, even a small bug, a small something that happens, there is 10,000s of cores interacting with each other. So it's very easy to get a bug exposed, okay? So it's not correct, it's very hard to run on the GPU, okay? So I went ahead, I tried to implement it on the GPU. I actually spent a lot of time because it's so hard to like write things on the GPU. That's one reason like why HVM is so interesting, like give access to the GPU to people. But like working in CUDA, working like OpenCL, those languages so hard. I spent so much time like on this, I guess, 2 weeks trying to get this running on the GPU. But I managed to, this is a big file, and then like I run on the GPU, and like this version, okay, this version here, okay, that's 3 times faster than the HVM1, is running at 90,000 real writes per second, okay? It's just a metric of like how many things are happening, okay? Sorry? Yes, sorry, 90 million rewrites. Speaking numbers in English so hard to me still, sorry about that. So, okay, I will write the numbers just to make sure I don't get it wrong. So, CPU, HVM2, 3 times faster than HVM1, 90 million, okay? So run same computations on the GPU. First try failed, second try failed, third try failed, could not get it to work. Sit down, breathe, think about what's going on, think about the parallelism, synchronization, the interaction between threads, come up with a new solution to synchronizing those things, write down that solution, implement it, fail. So I spent a lot of time like in this loop of trying to implement, trying to get it correct, failing. I spent so much time that I even wrote a paper, okay, about like this new algorithm that I had to make it work like in parallel, in massive parallel fashion. So I call it a lock-free interaction combinator evaluator. It's not a complex algorithm, like it's not something that deserves a big paper, but it's something that was never described before and that you need to get right, because if you get anything wrong, it will not work. So I like explain this paper how you can like solve the problem of like having those overlapping regions where threads collide with each other and bugs happen. So we shorten the area that the threads can rewrite, can influence, and then we have like this very synchronized step where like one thread does something, another thread does something, and they do it in a lock-free fashion. And like after, I spent a lot of time doing that, and like after the 10th or something attempt, I managed to run it on the GPU, okay? And it went from 90 million to 700,000 million. So 10 times faster than the CPU. So I was very happy, like it's a new record, like much faster than before. And then I spent the next days improving, and we reached a peak of 2.5 billion rewrites per second. So that's a lot of like graphs interacting in a single second. That's a lot of triangles interacting with a single second. So I was very happy about this result. That was, let me make the division. So 27 times faster than the CPU, HVM2, which means like it was 80 times faster than the HVM1 would be on the same computation, okay? So 80x, okay, of what we had on the HVM1 that was competitive with Haskell in many benchmarks. I mean, 3 times slower because some Haskell guy managed to make it much faster, but yeah, so we have something that is much faster now, and that's very promising. That's very exciting because, okay, now we can take those high level, like those high level, those low level, those like all kinds of programs that do a lot of like expression, pattern matching, blah, and run on the GPU without any effort from the programmer. Just give it to the HVM does it magic, and now like anyone has access to massive parallelism. So that's very cool. That's very cool. That's new. And I mean, the fact that it like worked with like thousands of threads and reducing huge graphs, it's very cool. Like because very hard to get it right, and it kind of means that it's very likely that the algorithm is correct. Okay, is it correct? I can't say for sure. Okay, I mean we don't have a formal proof yet, but like it's working very big tests with thousands of threads, so that's a good indicative that we are in the right path, okay? So I think simplifying the HVM was a good decision, and that's kind of the moment that we are now, okay? So the HVM has been simplified, implemented it on the GPU. We are trying to implement it multi-core on the CPU too now, okay? That's kind of what we are trying to do in this meeting on this place right now. It's not entirely necessary because, I mean, the point is to run on the GPU, but it's also good to have a parallel version on the CPU, okay? So that's the moment that we are now. So what's the current plan? Okay, what's the future of the company? Okay, so first, let's finish HVM 2.0, okay? Make it solid, make it fast, make it correct, give support to many languages, like make something that someone can just download and use it like in their languages, in their problems, and blah, blah, blah. Like let's make it production ready and let's launch it for the community, okay? So that's what I try to do right now, okay? And then once people are using it, once like people are seeing the value of like that HVM can finally bring to the world in this production-ready version, we'll try to be looking for applications. Okay, so the first application that we're gonna cover is Kindalia. Okay, so the idea you all know is pretty simple. Take the concept of Ethereum, a peer-to-peer computing network. Instead of having the HVM, have the HVM, and now you have a much increased computational capacity without needing to resort to like complex crypto primitives and a lot of like complex schemes. No, just because of the raw computing power, we can like make it hundreds of times. We can make hundreds of times more computations per second in the blockchain. It's not good to say transactions per second because transactions also depends on the network, depends on the consensus, but 10 times, like hundreds of times more computational operations per second. That's the idea of Kindalia, which would allow us to like have things on a layer 1 that's not possible to have on Ethereum today. It would allow us to serve a very fast modular VM for layer 2 that's like outperform the ones that exist today. Okay, so that's the plan we have. The first application that we have for the HVM, Kindalia. The second application, also very important, make it something that other languages can use, okay? So the idea is, first, let's take all those functional languages, Elm, Haskell, Idris, Agda, and let's compile them somehow to the HVM so that Haskell programmers, Idris developers, Elm developers can run their programs in thousands of threads on the GPU. That's a very cool thing. That's a very good project. But the main problem of that, it's very complex because those languages are very complex. So there are too many features to cover. Like Haskell is huge. Like so probably will take a long time to like compile all of Haskell to the HVM. Elm is easier. And the good thing is that there are many cool functional programming languages that have a small core, like Idris, Agda. I think compiling those pure script, I always forgot pure script, but like that would be simpler than Haskell than to compile to the HVM. And also, like we can be a little bit, what's the word? Okay, I forgot the word, but like ambitious. Okay, we can be a little bit ambitious and try to also compile more like non-functional languages, imperative language like Python, JavaScript to the HVM. That would be very cool because like something very nice that happened recently, that is this new Mojo language that's pretty much a Python-like language. It's not Python, it's just Python-like, and it compiles to very fast single core C code, okay, assembly code. So pretty much a faster Python. And they managed to raise 100 million in a round to make this language, to develop this language, and like for people to use it for AI, for like everything that Python is used for today. And that's good because it's not Python. It's a Python-like language. So like perhaps you're like, oh no, we need to give support to all of Haskell. Perhaps you don't. Perhaps like all we need to do is support something that's Haskell-like, kindlang, support something that's Python-like, so we can make our like Kydon, like Python-like language that compiles to the HVM. We don't need to give support to the strange things in Python that make it so hard, but those things nobody's using anyway. So like perhaps very quickly you can have a Python-like language that compiles to the HVM and then is running on the GPU. That's something that I think developers would love. I mean, I would love. So perhaps that's something that we can try, okay? And a lot of people would be using it. And we can sell programming languages, but like they raise a lot of money to develop a programming language. So we need to understand what the business is there, okay? And we also need to grow a lot in the business sense because if they raise it, there's a market there, okay? And it's very similar to what you're doing. Like take a programming language and make it faster, okay? let's learn, okay, what's going on there, what's the market, what's the business. And like if you have something that can take Python and run it thousands of times faster than that, yes, we have something with a lot of value. We need to be able to convert that value, okay, in like actual like financial value, I guess, as a business. And like a final application that I think we should be looking at is AI, okay? Of course, like everyone's talking about AI, so like kind of the hype right now. But there is a good reason, I think, that we should be looking at this, okay, as obvious as it might sound. And that's the fact that why AI is so trendy right now, why it's so popular. It's because of results. GPT-4 is just too good, okay? Everyone's using GPT-4 every day for everything. I use it for everything. Like I can do 2 times more coding with that. So it's good, it's real good. And why GPT-4 is so good? It's not because it's a new algorithm that's better than everything else that exists. I mean, we have neural networks since decades ago, okay? And we have LLMs like since 2013, I don't know, but like 7 years, okay? So what made it so good? Scale. They just took this algorithm and put a lot of GPUs on it, a lot of money, burned a lot of computation to make those models real good, okay? So, also more data.
Insane amounts of data.
Yes.
Like that.
Okay, sure, but also like the compute to train on all that data. So scale, you can just shorten that as scale. They scaled the algorithm. And the thing is, we have many algorithms on the literature. I'm not claiming we will be inventing algorithms here, but we have many existing algorithms on the literature that are better than neural network in many cases. And nobody scaled them. Like nobody tried to take some like evolutionary algorithm, some symbolic AI algorithm, some Bayesian network, I'll never pronounce that right, sorry. Some like proof synthesis, like those AI algorithms. Nobody has taken those algorithms and like throw thousands of dollars in GPUs to scale them, to train them. Why nobody has done that? Because you can't do that. Those algorithms run on the CPU, and it's very hard to get those algorithms on the GPU. Like especially if we're talking about evolutionary algorithms and like symbolic AI, that's very functional, okay? So if now we have something capable of taking a functional algorithm and running it on the GPU, and we give that to researchers and to people that work on those algorithms, perhaps they will be able to compile those algorithms to the GPU, and who knows if those algorithms will perform better than LLMs? No one knows. I mean, perhaps they will not. Perhaps LLMs are like this better, God-like algorithm that nothing can outperform. But perhaps LLMs are good just because we scaled them. Let's try to scale those other algorithms. And HVM can do that, okay? So that's the third application that I think we should have a like very strong eyes on, because that has a lot of potential. Does not mean it worked out, but it has a lot of potential, okay? So yeah, I guess that's it for now. That's the overview of the hardware company. In short, the goal, the mission of the company is to take the technology, the insights that we have gained from the interaction combinator, interaction net model of computation, and turn those insights in a practical runtime that's capable of massive parallelism, okay? That's something that's very aligned with the future of humanity, because CPUs, GPUs, now like everything is using so many cores, so many threads, and bring that massive parallelism to developers by like using by compiling to programming languages, by like doing those peer-to-peer networks that use like HVM on its core, by serving that to AI developers, okay? And with that, we can like finally extract the value of interaction combinators and use that like to bring the massively parallel future of computation to humanity, and hopefully find ways to turn that into a strong business, okay? That's the heart of the higher order company, okay? Does that make sense? Was that clear for everyone? Yes. Everyone's on the same page?